All right, hi people. Today we're going to be doing supervised learning, and this covers the first 2 weeks of what we learned in our AI lectures. So it goes over what is supervised learning, along with things like gradient descent, cost function, and then doing things like logistic regression and the k nearest neighbors algorithm as well. So it is an exhaustive list on all things supervised learning. So, firstly, oh, I guess that's deciding to play now. All right, cool. So, firstly, how do I? Okay, there we go. So we're going to look at some types of machine learning. So, can anyone tell me what is the difference between AI, ML, and DL? So, artificial intelligence, machine learning, and deep learning. These aren't the same thing, but can anyone tell me what they are and what the difference between them is? Yeah, all of supervised learning. Can you imagine, Victor? Yeah. But yeah, can anyone say the. Does anyone know? Got any definitions? AI, ML, and DL? ML is the process of training the model. Mm-hmm. Yeah. Kind of. So, AI, artificial intelligence, in the definition, is just anything that's done by a computer that imitates intelligent behavior. And this is like a very broad term. So AI doesn't necessarily have to be anything specific. Like if it appears intelligent, it can technically be classed as AI, which is why you hear all these companies chucking around the buzzword, oh, AI enabled, AI hosted, AI empowered, this and that, because there's no like um, objective definition. It's a bit subjective, but that's what AI is. ML, so machine learning. So machine learning is a subset of artificial intelligence that can learn and improve based on training data. So it learns based on the data it's given and it can improve based on the data that it's given. The more data you give it and the better quality that data, the better the model will perform and do what we want it to. That's what machine learning is. And now, deep learning is another subset inside machine learning that deals with neural networks. Neural networks Neural networks are the imitation of the human brain. Our brain works with various interconnected neurons, all firing signals at each other, and humans aim to replicate that in software, and that's what we call a neural network. And surprisingly, they're quite good. It's what really popular AI software like ChatGPT and most image recognition software, they run on neural networks and deep neural networks, meaning they contain a lot of hidden layers. You take inputs and pass it through a lot of series of interconnected nodes like neurons, and they produce the output. So that's what deep learning is. So AI is the broadest term, ML is a subset of AI, and DL is a subset of ML. Hope that makes sense. So where does supervised learning fall into this? Well, supervised learning is a machine learning application. However, it's not deep learning because we're not making or using a neural network here. We're using kind of statistics more than neural networks, which is kind of what Shay's put in the chat right here. Lovely meme. I've seen that on LinkedIn somewhere before. I'm pretty sure you sent it to me. And that's where supervised learning falls, and it allows a model to train and learn from pre-labeled input data. And this is where it's truly different from unsupervised learning, right? So unsupervised machine learning is when you train it without labeling the data. You just give it some data and ask it to figure it out. However, we're much kinder when we use supervised learning because we're like going through it and teaching it what we want, what we expect, and therefore it's better. When we want to get some desired output, we always strive to use supervised learning. However, it's not always possible. it's not always practical because labeling and collecting data for supervised learning is a long and expensive process. We're talking about billions and billions of data points. It would require a lot of time and money to label all of them and collect this kind of data. Hence, a lot of models are trained on unsupervised, which is you just can scrape data from anywhere, such as the internet, and just pass it into a model, which is what we learned later, such as k-means clustering. That's all unsupervised. So when we have this pre-labeled data, we can just before we move on, actually, I wanted to talk about reinforcement learning. So that's basically when you have a reward and a punishment, and you have a model doing random actions. And every time it does an action that increases some kind of score or whatever you're trying to maximize, you give it a reward, and therefore it does those actions more and more. It's kind of like how you teach kids with like reinforcement, like you reinforce good behaviors by rewarding them, and then you punish bad behaviors so they get some score taken away, and therefore they're less likely to do the things that are giving them a punishment. So going back to the supervised learning, so there are two types of supervised learning. So we within supervised learning there's classification and regression. So for producing discrete class-based outputs, we'd use classification. A very common example used in the industry is the detection of breast cancer. So if you have a mammogram or some kind of histology slide and you'd like to identify whether it's cancerous or not, you want to use a classification algorithm, as you want to know, is it cancerous or is it not? You don't want a continuous answer like, oh, zero point 0.5. It wouldn't make any sense, right? So that's when we'd use classification. The other kind of supervised learning technique we can use is regression. And this is what we'd use for producing continuous data outputs, such as if we're trying to predict stock prices, it makes no sense for us to classify them into good or bad. We kind of want a definite number of what it thinks the stock price will be in how much time. So that is an application of regression as opposed to classification. So anytime you formulate a supervised learning problem, you have a task and a goal. In the case of supervised learning, I'm just going to generalize it. So you'd have some input X, and if this is called the feature, the input that you give it, that's called a feature. Normally you have multiple features, and you represent this as a column vector, hence why it's called the feature vector, which is populated by all the individual features, and predicting the appropriate output y, which we call the target. So we give it an x, it does its function, and it gives us an output y. X is the independent variable, and therefore y is the dependent variable because it's depending on what x was. Okay, so once we have a task established, we need to have the goal, right? So the goal of regression is to find a function f such that f of x is equal to y. All that means is we're trying to calculate a mathematical equation or a function that will basically turn our input into the output, and do that in the vast majority of cases. If we have that, we have a successful regression model. With classification, it's the same as above, but the output is just discretized with a nonlinearity. And we'll look at discretization and nonlinearities later, but in this, essentially, classification uses the same process, but passes it through an activation function as well, which is what discretizes it. But more on that later. So, when we have a machine learning model, the first thing that we need to do is train it. So, for the best results, we need a large quantity of input-output pairs, and this is what we call labeled training data. We give it the input and what the output would be for that example, hence labeled. Then in an example like simple linear regression, where it's just like a line of best fit, straight lines you can remember from like even GCSE maths, you would have a scatter diagram and you'd have to draw the line of best fit. So we bring it a bit more up level than that. So we can learn, as we learned in A level, we can use a mathematical formula to calculate the line of best fit, and that would be 100% definitely the line of best fit. We don't need to just judge it by looking at it. So this line is actually not calculated by the formula that we learned in A level maths for calculating the line of best fit. It's done by a process called gradient descent, which we're about to do next. But the reason why I was always confused at the start, why can't we just use the formula, right? It makes a lot more sense and it's much less computationally expensive. The reason is, well, that formula we only learnt it for linear regression, not quadratic, cubic, and high dimensional polynomials, right? Um, and that the reason is because formulas like that don't exist for the higher dimensions. And as you get to like 37 order polynomials, which are like really complicated, has lots of curves and etc., you can't really find a line of best fit. It won't work. Hence why we have to use processes like gradient descent. Um, and basically the process is the line is found by projecting a random line, any line, onto the graph, and then it's just adjusted, constantly fine-tuned, as the word is, by adjusting the hyperparameters. Sorry, not the hyperparameters, the free parameters. And in the case of a straight line, linear regression, we have the general equation being y equals mx plus c, as we all know. So in this case, the free parameters are m and c, aka the gradient and the y-intercept of the line. What we call y and x are the fixed parameters because we can't adjust those values. Those are the values that are taken by the graph. The graph like gives us those values. We can't adjust them. The values that we can only adjust is m and c, and that's what is adjusted to find the line of best fit. And now any predictions just uses the line and interpolates or extrapolates it. So in A level, if you remember statistics again, there's a lot of A level recap going on here, but we just with lines of best fit, you can then do linear interpolation and extrapolation, which is basically what we do. We just are given an input and then we find where that what's the value of y by the equation of the line of best fit, and that's the output we give out. So it's just a case of linear interpolation with that. And that's actually the case with higher dimensions as well. We have a line. What we're doing in predicting is basically just a statistical method. It's just linear interpolation or extrapolation. Nothing more than that, even with the higher dimensions. Does anyone have any questions so far, actually, before I move on? I know I've said a lot. Does anyone have any questions about machine learning, formulating supervised learning problems, or training? Or are we all good? I don't want to just be talking at you. So can we get some stuff in the chat, like what we're thinking? Good? Any questions? All good? Okay, cool. Great, okay. So this function clearly defines a value. So, okay, thanks, guys. So next thing we're going to look at the cost function, right? Or sometimes we can call it the loss function. So this is a function that just defines a value that gives us how wrong our model is in basic terms. So as our model makes more accurate predictions, the cost function would actually need to decrease. It's a measurement of how wrong we are with our model. So naturally, we don't want to be wrong. Being wrong is bad. So we want to minimize that, and that's the point of gradient descent. So in order to have an algorithm that works like gradient descent, it's only as good as the cost functions that we're using and how well representative they are of the accuracy of our model. So there are three types of cost functions that we need to know about. One of them was absolute value loss, which is pretty basic. The only reason why it's not really used anywhere, but the reason why we need to know about it is because it goes into the next one, which is mean squared error loss. So as you can see, the mean squared error loss is just the absolute absolute value loss squared. And what this is we call it L2, by the way, and the absolute value loss was L1. And this basically takes a loss value and squares it, and this gets rid of negatives. That's all. That's mainly its purpose. One, it obviously makes the values bigger, which increases the importance of it to any algorithm, which is good because we really want to decrease the loss as much as possible. But also, it makes sure that everything's positive, so it doesn't cancel each other out. If we had the absolute loss value though also is modularized, so that's also positive. The only reason why we can't have like negative values of loss for any of these is because if we're computing loss for each data point, and one of them's negative and one of them's positive. When we average it out at the end to give like the loss for the model, they'd cancel each other out, which would be bad because they were clearly wrong. But if they cancel each other out and we get a loss near zero, that's indicating that the model was good, which we don't want. Hence why they all have to be positive in order to accurately give a loss measure. The final loss value is more of like a discrete value. It's 0/1 loss, which is basically zero if it's equal and else it's one. So it's not a very good measure of loss. It's there because it's one of the methods, but I don't really think it's used anywhere because it's not really practical, because you're never going to have a f of x value that's exactly equal to y. That's impractical, and therefore there's no way of measuring how correct you are. So just beneath that, I've written the use cases. So mean squared error loss is often used for regression, and a form of 0/1 loss is sometimes used for classification in very specific niche cases, but not really. We use another thing called the cross entropy function, which we'll learn about later for classification. Finally, the big algorithm, gradient descent, the pinnacle of machine learning. So this is basically a general strategy to minimize cost functions of complex models, but it's used for simple models as well. So just any model. And as I explained, we can't always use the mathematical and statistical formulas because there is no formula for the high dimensional ones. And all this does is it basically plots a graph, every combination of three parameters, so like the m and the c value, you have a certain combination of them. So m can be 1, c can be 1, then m can be 1, c can be 2. And all of these combinations basically is plotted in a 3D space. So the combinations of three parameters is plotted against the overall cost for that model. So every combination of three parameters is defined as a model. So if you have y equals 2x plus 3, that is a model. And that model has its own cost. So every single model has a cost, and this is dictated by the three parameters. When we plot this in a 3D space with the cost value of each model as the z-axis, we can then have the objective to minimize the z value and therefore minimize the loss, which we have a better representation, a visual representation on the next slide. So this is some pseudocode here, which very nicely and simply describes what or how gradient descent works. So as you can see, there are two parameters that gradient descent takes in. So obviously it takes the data, the input data, the features, and the other thing is the learning rate, which we'll get onto in a sec. So first, it would start at a random point, which means a random combination of parameters. So it chooses a random data point. So it could be any value of M or C if it's linear regression. And then it'll run the next process repetitively. So I've used a do while loop post-test iteration here. So use differentiation to calculate the direction of the steepest descent of loss. Then once you work out which direction is the steepest descent, you then take a step off the size learning rate in that direction. Finally, once you've taken the step, you update the three parameters to the values of the new point that you're at. So the new point that you're going to move to is going to have its own combination of the three parameters, aka its own model with its own cost function, which will be lower than where we were before because we moved down. So now we just do that again and again and again, while, and now this is the while condition, the change in loss is occurring. So what that means is all the directional derivatives from the point is not zero. So if you were there in my session yesterday, we looked at how to calculate directional derivatives. So if you are at a point on the graph where the directional derivative in every vector direction is zero, then you call this the convergence point, aka it's kind of like a local minimum or even a global minimum. Hopefully it's the global minimum. So that is the point where the algorithm would end the while loop and you'd return the free parameters, aka the model that's been optimized for the data set, that's been perfectly trained. However, we look at it that we don't want to always just minimize the cost as much as possible because that leads to something called overfitting, but that's again covered later. Does anyone have any questions while we're on this about gradient descent or like the cost functions we looked at? All good? Okay, cool. That's good. Hopefully, that's a sign of me explaining it well rather than no one's paying attention. It could be either way when everyone's like, all good. Okay, cool. Um, just to not bore you all to death, I've included some colorful diagrams here. So this is a visualization of what gradient descent looks like. So in the upper image, the vertical axis is the loss. So you can actually very easily see this right now in 3D space. That it's a concave shape, and this is super important. Every time we have a gradient descent algorithm, it works. The visuals, yeah. Every time we have a gradient descent algorithm, gradient descent, as a fact, works optimally with concave shaped graphs, aka like the graph we have over here. The reason is because there's no like bumps that could lead it to getting stuck inside a local minimum, and it's going to find the global minimum really, really quickly. So this is the optimal kind of shape for a gradient descent algorithm. It means that we're going to find the global minimum really quickly, no questions asked. So the loss value is how we go down. What is it? Shay with the memes in the chat. Love that. Keeping the attention. Um, the lower image, however, so this image at the bottom shows how we can have models with many features. So you can see we have y equals w0 plus w1x plus w2x squared plus w3x cubed, blah, 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 all the way until wmxm. Altogether, we call that the feature vector. So you can see like the feature vector is w0, w1, w2, blah, 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 blah. And then we have another vector called x, which is just 1x, x squared, blah, blah. So if you dot product the feature vectors with those x values, you get the equation for this model. So you may notice that there's obviously a lot of different terms here, and do we need all these terms? Quite often the answer is yes, but also it could be no. So we need these parameters, all of the parameters of the most or the highest order model, we need them in our gradient descent space. So whatever model we have with the highest number of features or the highest number of um, W basically um, that exists in our range of models that we've tested, we need to have that many dimensions in the gradient descent. And there are going to be models that didn't use all of the parameters. For example, we might have had a little linear model here. It would be very bad. It would have a very high cost value, but it would still be one of the models. So if we had a linear model, it would still have all of the parameters after it in gradient descent because those features need to exist. However, the coefficients, so the W values, would just be zero, making them basically negate, like go to zero. So that's how it would work. But yeah, so the dimensions of the gradient descent always takes the dimensions of the model with the highest number of features or terms, basically, highest order polynomial. Hope that makes sense. If not, don't worry, it's not that important. It's quite a very niche specific thing that I doubt we're going to get asked in the exam. But the main thing you need to understand from this slide is how gradient descent works and what this shape is. How do you choose how many orders of polynomial terms to have? Do you mean like how do you choose how many models to have or how many like terms to have in the polynomial? The m value. How do you choose the m value? Well, you try loads of different m values. Each of those would have different cost functions, and you'd pick the m value which gives you the model with the lowest cost function, which is what gradient descent does. Elbow method? No, no elbows here. No. What do you mean? I don't understand the question. What are you asking? This is we're not clustering. We're mm, oh, how would you choose the K? Are you asking? Okay, yeah. Elbow method is used for unsupervised learning when we do k-means clustering. However, that's not a supervised learning technique, so we won't be covering that today. It doesn't depend on the domain, the number of dimensions. Doesn't it depend on the? Doesn't it depend on the domain? What depend on the domain? Would it be easier if someone asked the question in on stage with the mic rather than typing it out? If you want to request, and I will get you onto the stage. Yeah, I guess if you can do the training validation set to make sure you don't under. Right. Okay. Is this questions about what we've just covered, or are we? Why are we to? Okay, we'll get to all of this stuff, but we're not there yet. In fact, the validation stuff is all in unsupervised um learning. Has to choose the number of epochs. Oh, okay. How to choose the number of epochs. Um, so that you just get by seeing uh, when you'd minimize the cost. So um, to calculate the number of epochs, what we do is you choose you just choose until the loss is however low you want it to be, I guess. You choose until you keep doing epochs until the performance with the testing data starts to decrease. So at one point you'd have the creme de la creme. At one point you'd have the best optimal like cost, right? Which is the lowest possible value of cost that you can manage. And this we do with the test data, not with the training data, because the lowest possible value with the of cost for the training data would lead to a severely overfitted model. That's why when we look at performance and we want to judge how many epochs that we want to run, we do it with the training data. So every epoch, our model will get more and more and more fitted to the training data. And then once we test this with the test data, we'll eventually start getting better and better performance, so lower and lower cost, until we reach a trough, and then the cost starts increasing again with the test data. And this is because the model is now starting to overfit. So that's how we decide the number of epochs. But we're not on epochs right now. Gradient descent is like different. Gradient descent does not rely on epochs. Gradient descent is simply designed to decide which model of uh, we decide which model out of all the models that you produced is the best. Does that make sense, people? Okay, cool. Glad that's all cleared up now. Great. So, the effect of the learning rate on the result. So, you may have remembered that I mentioned the learning rate. It was one of the hyperparameters that we needed to pass in to the gradient descent algorithm along with the data to make it work. So, the learning rate is just the distance or the step that the gradient descent algorithm takes in the direction of steepest decline. So if we have a gradient and we've decided the gradient vector, by the way, is the vector that points in the direction of the steepest gradient. So we always want to go in the opposite direction to the gradient vector, which we kind of looked at yesterday with gradient vectors and directional derivatives. However, we're not going to go into specifically how to calculate those out today. If you want to look at that, there is a recording of yesterday's session I did. So with the gradient vector, once you have it, you go in the opposite direction to it by the step of the learning rate. So the learning rate dictates how far you go. And this has consequences on the result we get from our model. We could end up with drastically different minimal cost values depending on the learning rate we give it. And it's very important to find the right one. So also, I've been using the term hyperparameter. I just wanted to clear up what that means. A hyperparameter is kind of like a setting or a configuration of a machine learning model. And pretend you have like an app and you are trying the app, I don't know, does something like you're playing a game, but then you have something like the settings menu where you're controlling the FPS or the sound or the dark theme, light theme, etc. Those are like the hyperparameters. They affect the model, but they're not inertly like involved in the data or the output. So hyperparameter adjustment is like adjusting the configurations of how the model works, how the algorithm will behave. What's an epoch? An epoch is just an iteration. It's just literally a fancy word for an iteration of a machine learning model. Does that make sense? Or yeah, cool. All right. So finding the correct learning rate is crucial as they affect the results. And here is how they affect the results. So if the learning rate is too high, the point could actually end up bouncing out of the trough of the local minimum and overshoot, causing the algorithm to diverge. And I can kind of, can you guys see my mouse on the screen, like where my mouse is? Or can you just see the, like the PowerPoint? Can you see my mouse moving around on it? Yeah, okay, cool. So imagine you're inside here, inside this visualization of the gradient descent algorithm here. If your learning rate was, say, from a massive one, because we looked at if it's too high, the learning rate is too high, then what it is if we move from here to here, let's say, we've just missed the minimum and gone all the way here. We could even start off at a point that's very close to the minimum. Like we could start off here somewhere. And if our learning rate is very high, we'd move in this direction, but we'd move so much that we'd end up over here, which is obviously in a much worse off space than what we started with. Modeling. Yeah, that do be like that. Nice one. So yeah, that's why we don't want a very high learning rate. It would mean that we end up from here to here and it'll be bad. We will just bounce out of the minimum, causing divergence. That's the word. If the learning rate, however, is on the other end of the spectrum too low, then it significantly slows down the algorithm and means that it can easily get stuck in small troughs and dips, thinking that that is the local minimum. So we can't unfortunately visualize that in this concave shape gradient descent because, as I said, this is the optimal form of it. So no matter how small the learning rate is, in a concave shaped gradient descent, it will always get to the right answer. However, if imagine if we had like a more bumpy shape, such as like, I don't know, something quite bumpy, let's say like the palm of your hand. Visualize us doing gradient descent on the palm of your hand. You have a lot of grooves, a lot of bumps on the palm of your hand, but you want to find the local minimum, so the lowest point on the palm of your hand. If you were to say go in the ridge between your fingers, that might appear like the lowest point at that point. If your learning rate is small, it won't be able to bounce out of that local minimum and then get to the global minimum. So a learning rate being very small means one, very slow progress. We don't want that. We want some element of speed and like yeah, speed basically. It will be very slow if you have very small jumps. But we also don't want it to get trapped inside local minimums and then assume that that is the global minimum because naturally we can't visualize it like this all the time. It's a very intricate shape full of bumps, so it it needs to be the perfect learning rate. Otherwise, we'd get stuck with a tiny learning rate inside a tiny crevice almost that isn't the global minimum, but the algorithm would think it is because it is a minimum. And according to the algorithm, we stop whenever the gradient of steepest decline is zero. So in any local minimum, the gradient of steepest descent would be zero. So if it ever reaches a global minimum, we're stuck there. But a local minimum would be stuck there with a very low learning rate. Um, Other than that, we can observe the loss against epochs during trading for each learning rate. So this is what it's saying with the epochs. So basically, with the hyperparameter, we can actually dynamically adjust it. And in fact, there are a lot of gradient descent algorithms that exist nowadays with dynamic hyperparameter adjustment of the learning rate. And this means that it actually adjusts the learning rate as per what it sees as it runs the gradient descent model over many epochs. So naturally, it'll do one, it'll have a random learning rate for that, and then it'll do another epoch, starting at a different random location with a slightly different learning rate, and that will hopefully produce a better result, and then it'll know that the learning rate was better in this model. And doing that for multiple epochs from different random points in the graph kind of lets us see what the optimal learning rate is and also increases the chance that we actually find the global minimum rather than just a local one. That's why we never run gradient descent once, we run it multiple times. And this is what I meant by an epoch. You run it for multiple iterations. And this produces hopefully, a bunch of different minima value. And then you can choose your pick. You can choose the lowest of the minimum you get. And that is likely to be the global minima, as opposed to just doing it once and hoping that's the global minima. However, the exception is when you have, again, this concave shape. Gradient descent loves this concave shape. If you have a concave shape, you only do it once because, well, you're always going to end up here. There's no local minima or bumps anywhere. And we'll look later at how activation functions actually are built to enable the graph to look as concave as possible. That's why the cross entropy function exists in the first place, actually. But anyway, so that's actually gradient descent covered. Does anyone have any questions about gradient descent? I know this is kind of getting a bit theoretical, a kind of bit like imagination is required. So even the palm of your hand is required. So does anyone have any questions about gradient descent or the learning rate or epochs or anything like that before I move on to the next slide, which is on fitting of machine learning models? I'll give like 10 seconds for anyone to ask a question. Okay. I do. Let me type it. Okay, wait. Someone has a question, but I can't see. Oh, it's Ashpree. I remember. He doesn't have a name or a profile picture. What a guy. What's your question, Ashpree? If you want, you can come onto the stage and say it as well, if it'll be quicker. If we have if we have w to the t x, how do we gradient descent in the maths? What do you mean? Like, what do you mean in the maths? We work out. Do we just differentiate? Yesterday's. Were you there in yesterday's session? Well, actually, going off of that point, Shay, we don't actually apply the dot product to work out the gradient vector. So no, we use the dot product to work out the directional derivative. Remember, I said something yesterday which isn't totally accurate, which was the gradient vector is the same as the directional derivative. They're slightly different. Directional derivative is the gradient in a direction of our choosing at a certain point, whereas the gradient vector is the steepest direction, the gradient, so the direction of the steepest gradient from any point, because the gradient vector gives us a gradient, sorry, a vector, so it's a direction it gives us, whereas the directional derivative gives us a scalar value of the derivative any direction we choose. So the gradient vector always points in the direction of steepest incline from a point. So it's true that if we were to calculate the directional derivative from a point in the direction of the gradient vector, we'd end up with the highest directional derivative we could possibly have at that point. Does that make sense? Or am I confusing you guys now? How do I know which direction to go? I don't really get used differentiation. Okay, do you want me to like do a practical example now? Like we can stop, pause this lesson, and do like a practical example of how you would work out the okay. All right. Uh okay. Unplanned interruption. Right. Okay. Let me get my drawing tablet out. I'll do it. Okay. Are you guys happy if I use the example from yesterday? Okay. All right. Let's see. Right. Where is my mouse? Oh, yeah. Okay. Right. Okay. So, can you guys see the screen? Let me just check the recording is also seeing the right screen. But can you guys see my notepad now instead of and Discord's also gone. Okay. Okay. You guys can see the notepad. Okay, cool. All right. So, um here, let's say we have the equation f of x, y, and that equation is what was it yesterday? X squared plus 3y cubed. I think that was the one from yesterday. If not, no worries. But like we can just do it with this. So this is a 3D. This is what we represent in a 3D space. Um, so we have the fxy value, which would be the z-axis, kind of the x value, x-axis, and the y-axis. Okay. Um, oh, if you're confused about why this is 3D, it's because f of x is equal. Sorry, f of xy is equal to z. Just as how we say f of x is equal to y, f of xy is equal to z, meaning that the only two independent variables is x and y, and z is a dependent variable because it's dependent on the value of these two, and we apply the function on it to get the value of z. So z isn't actually an independent variable. Hence why we can just write it as a function of its independent variables, and we can treat this instead of z. We can call it loss, right? In fact, let's change it from function f to function l. All right. So this function l gives us the loss, okay? And the loss is now calculated on these two um, fixed parameters. So we have x and y, but naturally we can assume there's a 1 here. So if we say the formula was loss is equal to m, or like a x squared plus by cubed. All right. So this would be our model that we're working with here. Ooh. This would be the model that we're working with. No, actually, that would not be the model. That would be the general format. And this here would be the model, aka the format, and it takes a specific version of the free parameters. We have a specific value, so this produces a graph in 3D space, and this graph is exactly what we're going to traverse. So we want to minimize this value, which is the loss, right? Let's get started. First, do we remember partial differentiation? We want to partially differentiate these. So we have delta L, delta X. Let's do with X first. We end up with, do you remember partial differentiation? We treat every other variable as a constant, and we only treat the variable that we're differentiating with respect to as the variable in partial differentiation. So here it would just be 2x. Then, next one, we want to partially differentiate with respect to y. So that would be that, and we'd end up with 9y squared. Does everyone understand where I've got these two values from? with the differentiation to x, there's no x values in this term here, so it goes to 0 as we're treating all of them as constants. And when we're differentiating with respect to y, there are no y values in this term, therefore it's treated as a constant and gets put to 0, as we do with any form of differentiation. Any objections with this before I move on? Everyone happy? Everyone on the same page with this? Okay, cool. Now, if we want to, why is it not scrolling down? Okay. If we want to find out the gradient vector, what we do is we write this out as the general vector. So it's 2x and 9y squared. And what we need to do is now substitute a value of a point. So so basically, when we find out, you guys are asking, how do we know which direction to move in, right? So this is kind of how. So we the value would be different from every single point on the graph. Because if you imagine it as that concave disk again, whether you're on the top left corner would mean you move right. If you're on the top right corner, it means you move left. So can anyone give me a specific point that we calculate the direction to move in from? Say this is the gradient descent algorithm now. Gradient descent. Gradient descent, as we saw in the pseudocode, I'm pretty sure I've spelled that wrong, but gradient descent. It picks a random point to start off with. So random point generated to start off with, as Shay has suggested, we'll start off with 5, 4. All right, that is the first point that we're going to start off with. Can we also get a learning rate, actually? What learning rate do we want? We'll go through like 3 iterations. Learning rate 3. Okay, let's call that 3. So alpha is the notation for learning rate, by the way, if you didn't know that. Okay, so now we have this. This is what we're going to use for the remainder of the gradient descent. This is the general vector. Now all we have to do is substitute the values in. So we have the first vector as being 10, because we substitute, I will write it in how it is just so everyone understands. 2 multiplied by 5, and then 9 multiplied by 4 squared. This is 10. And this is 9 times 16, which is 151, I think, right? Am I correct? Probably. If not, just pretend it is. Okay, 144. My bad. My bad, guys. My mental maths is not good today. All right. Okay, right. So this is now the gradient vector. From this gradient vector, we can now move by the learning rate to our next point. So the gradient vector is direction of steepest ascent. But we don't want that. We don't want to ascend. The gradient vector is giving us a shambles. We don't want to follow it. We go in the opposite direction. So what we want to do is, we move in the opposite direction. So we move learning rate multiplied by minus 10 minus 144. So Ashpreet gave us the learning rate, which was 3. So yeah, 3 is a very large learning rate. So in this example, we saw that the learning rate normally is between 0 and 1, normally, but we can have a learning rate of 3. There's nothing stopping us from having a learning rate of 3. And I respect Ashpreet's decision to have a learning rate of 3. So we shall go forth with the learning rate of 3. Minus 10 minus 144. So this would be minus that. So our next point would be um, it would be what 5 minus 30 and 4 minus whatever 144 times 3 is 1432. So now the next point we're at is 5 minus 30 is minus 25, and 432, 4 minus 432 minus 428. So we have now jumped from 54 to minus 25 minus 428. And this is generally why the learning rate stays between 0 and 1. Because, as you can probably tell, we have not probably missed the minima point, but we've also completely bounced out of the graph altogether. So let's try with a learning rate less than 3. But I just wanted to show what the impact, the destruction that is caused by having a learning rate that's way too high. If it's large enough, you can circle the graph and get to the middle from the other side. Go around the whole world kind of vibes, isn't it? Yeah, but the Earth's flat. Come on, guys. All right, so 0.49. Yeah, these are all values, good learning rate values. But yeah, that's kind of what would happen. So now we just iterate again. So we'd start off with this. So if we call this iteration 1, then we have iteration 2 now. So we'd start off with 2x, x value now being minus 25, y value now being 9 minus, oh god, okay, that's not gonna be pretty. Do you understand, or should I continue with this massive learning rate? Leave it. Okay, cool. So this is really in depth how the maths behind a gradient descent algorithm actually works. We have the loss function here. These variables here are these are the fixed parameters. We have the free parameter set, so this makes that a model. And then once we have a model, we can evaluate the loss for it, run it with a alpha of 0. You want me to do that, like, again, with a different learning rate, or like, do you understand? Yeah, I'm just conscious of the time that if you guys get it, we might just move back to the slides. Unless, like, you don't get it, in which case it's perfectly fine as well. All right. But yeah, this is how. All right. Where is using Twitch points on Discord? Does anyone else want to? Does anyone want me to go over it again with further iterations, or yeah? If I had a script to do this for me, it would be lit. But yeah, so the key points I think is just doing the partial differentiation, and then substituting in the values. And what you have to remember, very, very common mistake, so listen up, guys, is that the gradient vector gives us the direction of the steepest ascent. However, gradient descent wants the direction of the steepest descent, as indicated by the name. So we have to go in the opposite direction, aka negate this vector. All right, you have to remember to do that. Otherwise, you'll be doing the opposite thing. You'll be finding the maximum value of loss. You'll just be keeping on going and going until your loss is the highest possible value, and you pick the most suboptimal model that exists. So make sure you go in the opposite direction. You do not want to go in the direction of the gradient vector. It's just there so you can go in the opposite direction. It's like you want to run away from it. But like, does everyone? What? What is that image? Okay. Anyways, so no one said that they wanted to go over it. I've given like 30 seconds. So we good? I think we good. We're gonna go back to the slides now and continue. All right, all right. But glad you guys understand how gradient descent really works. Because I feel like before you get the maths behind it, it can seem like a bit of a black box that just takes inputs and gives outputs. So it's good to know how it's done. Perhaps we could even be asked a question to do it in the exam. Okay, right. Can I go back to the slides? Let's see. All right, so I'm assuming you guys are seeing the slides now. No, you're not. Okay. Why is why? Why? Okay, I'm assuming you guys are seeing the slides now. Okay, right. So yeah, this is where we left off. I'm hoping everyone's clear on this now. So I'm gonna move on. Fitting, right? How much? What time is it, by the way? I just want to check how we're doing for time. 2:58. Okay. Right. We might take a break in the middle of the session at some point. We'll do this like a proper big ass lecture. We take a break. Um, I have 1 minute to teach us everything. Yeah. Okay. Underfitting is basically when you haven't trained the model enough, so it's overly generalized, which leads to low accuracy predictions. Over appropriate fitting is the right thing. You should be doing this. So you train it for the right amount of epochs, and then if you keep training it, even after you've appropriately fitted it, keep on training it, and you get an overfitted model, which is basically when it's too adjusted to minimize the cost of the training data that it does not work when you try and give it anything new. It does not work. So here I have illustrations which I think make it quite simple to understand of what it looks like for a classification model on the top and a regression model on the bottom. Underfitting, appropriate fitting, and overfitting. um, Ashpreet's requesting a 2 minute break. If you guys would like a 2 minute break, please react to Ashpreet's message. I'm not. What? 2 minute break, I'm not. Overfitting. Oh, I've seen this one before. It's a banger still. We finished with gradient descent shape. We're on overfitting, underfitting, and appropriate fitting now. Okay, okay, okay. My bad. I didn't get the joke. I didn't get the reference. Okay. Um. So, would you guys like a break or not? Just like literally give me an answer. I will. Can someone put up like a reaction or like say something? I don't want to like bore you guys. I'm good for now. No, okay, cool. We'll continue. Good stuff. Right. So that's fitting done. Does everyone understand fitting? If you don't train it enough, you start training it. Remember, epochs, right? Epochs is iterations. If you don't train it for enough epochs, you'll end up with a highly generalized, underfitted model. You keep on running it through with more epochs, keep on optimizing it. You'll then have an appropriately fitted model, which works the best with the test set. And finally, you have the overfitted model, where if you're still not satisfied with appropriate fitting and you keep on doing epochs, then it'll be overfitted. Right. Next thing we're moving on to is parametric and non-parametric models. So I believe now this is the level up. This is now where stuff starts getting kind of complicated. So a model that summarizes. So what is a parametric model? Is a parametric model is a model that summarizes data with a finite set of parameters. Thus, this makes assumptions on the type of model, e.g., linear, quadratic, cubic, etc. Linear/logistic regression and neural networks are an example of parametric models. However, we also have another type of model, sorry, called non-parametric. And what this means is it cannot be characterized by a finite set of parameters. So it takes a variable number of parameters, and thus no assumptions are made. So you can kind of think about it as the parametric model. It goes in with its assumptions. It says, okay, I'm going to now create a model based on like five, six parameters. So that means it has what? Six terms in the polynomial. It's an order six polynomial basically, or it has six independent variables, whatever you want to say. But that'll be fixed. That is the parameter you've passed to it. Therefore, it's only going to create and test models that have six. All right, so that's parametric and non-parametric models. Let's move on to logistic regression. So logistic regression is a supervised technique that allows for class-based outputs, as I said, and it basically follows the same process as linear regression, but at the end it passes the outputs through a sigmoid function, which leads to them being classified. What do I mean by sigmoid function? Well, that we'd have to understand the concept of nonlinearities first. So a nonlinearity function is one that maps data so that it falls into two distinct ranges and very rarely in between. So we'll look at some images later, but that's what it's meant to do. That's what it's built for. It makes the data fall into two very small ranges that are far from each other and very rarely in between those two ranges. So to achieve classification, we are essentially applying the same principles of linear regression, but all we're doing with that is once we have the output of linear regression, we're just passing it through we're passing it through a nonlinearity, basically, which discretizes it. Um, and that leads us on to activation functions. So you may have remembered that I mentioned the sigmoid function in the last slide. The sigmoid function is just the activation function that's used for this specific type of model that we're learning right now, logistic regression. However, it's part of a set of broad functions called activation functions. And it's just a type of function that introduces a nonlinearity into the network, aka a way of separating a continuous range of values into two small ranges far apart from each other and rarely anything in between. Specifically, in this case, the sigmoid function takes a single argument and always returns the value between 0 and 1. And this value represents a probability. It's the probability of the data being classed into class 1. So you can call the classes whatever you want. You can call it cancerous or non-cancerous. However, in terms of the model, it's always going to be viewed as class 0 and class 1. And then it's quite easy to understand. Anything below zero point 0.5, less than zero point 0.5, would mean the probability of it being in class 1 is less than half. Therefore, we class it into class 0. If it's greater than zero point 0.5, it means the probability of it being in class 1 is greater than half. Therefore, it's more likely to be in class 1. So we class it in class 1. And in rare cases, if it's exactly zero point 0.5, it returns a decision boundary. However, it never happens because not only is it rare for it to get like an exact zero point 0.5, but we've also passed it through a non-linearity function, which specifically moves everything away from the middle and to the extremes. So, but just remember, in case they ask, if it's exactly zero point 0.5, you return the decision boundary because you can't exactly class it into one or the other. The function itself uses e. That's how we actually end up with this kind of S shape because of the e shape, e symbol here. We're putting e to the power of minus u, where u is the set of parameters. So sigma list of parameters, that would be the parameters basically. So you'd pass the parameters in, the parameters would be here, and all of them would then be sigmoided into either the top range or the bottom range, or if you're unlucky, somewhere in between. Which is, as you can see, that place is very steep, so you're hardly likely to get any x values, especially when you look at when the coefficients are greater. I want you to look at this blue line here. This is a extreme sigmoid function here, where you can say you're pretty much never going to get a value that's 0.5 because you're either going to get a value in this bottom range here or it's going to be in the top range. The probability of you having one here is a very small fraction of x. Do you guys understand activation functions, sigmoid functions, the sigmoid function and the concept of non-linearity? What are we talking about? Yes, yeah. Would you like me to move a little bit faster with it, or um, what are we thinking? We're almost done. After this, after cross entropy, we have to do k nearest neighbors, and then we're done. I did mention that it was going to be a really long session at the start because there's just so much to cover. But yeah, I'll just keep on going. Essentially, the cross entry function. So what I got from this is that we don't necessarily need to like know its exact bits. Like we don't need to know how it's worked out. We just need to know what it is. So a lot of the slides that we had in the lecture may have been like irrelevant because it was a lot about how we derived the cost function. All you need to know is that this is the cost function. It's arranged. So if you have y equals 1, it's you go with minus log blah 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 blah. And if you have y equals 0, then you go with minus log blah blah blah. Okay. And what by y I mean the parameter you pass in. So that's the class. Y is the class. Remember how I said you in classification you just classify it into class 0 or class 1. Y is that parameter, and then H would represent the parameter, the actual parameters you got, and um, the probability kind of. So in classification, fortunately, we don't have to rely on just a single class output, like, oh, this is class 1. The model actually also tells us what is the probability of it being in class 1. Is it definitely in class 1, or is it like kind of iffy? Say you had a probability that you got as 0.51. 0.51 would just about classify into the the class 1 category because it's above zero point 0.5. However, it could very well be, as a high chance of also being the class 0. All it is instead of 51%, it's 49%. So it could very well just be both. Hence, we always pass a probability when we have any kind of classification algorithm. So we give a class and then also the underlying probabilities so the user can understand how likely it is that we got the correct class. If something's a 51-49 split, it means it basically we're not sure. We don't know. It could be either. You wouldn't go do something because you have a 49% chance of failing, kind of. It's like that kind of logic. So yeah, that's basically all that this is saying. And then I've just explained here why we can't use the regular loss function. So remember how we had mean squared error loss before, which is what we used for linear regression. We can't use mean squared error loss for logistic regression because we passed the output of the logistic regression through a nonlinearity. Remember the sigmoid function. Once we pass not a continuous value through a activation function, such as the sigmoid function, it means that it's within two very short ranges, which does not work with the mean squared error formula. So it does not work with the mean squared error loss for cost, which is why we had to invent a different cost mechanism, the cross entropy. Because the reason why it doesn't work is because it produces a cost graph like this. And if you remember what I said before about gradient descent, um, if this was a gradient descent shape, if this was what the shape of the gradient descent looks like, you would get stuck in this local minimum and it wouldn't work. Then you get stuck in this local minimum and it wouldn't work. And then so on and so forth. So this is almost impossible to run on gradient descent if you were to pass a logistic regression with the mean squared error loss function. Hence, we use the cross entropy cost function instead, which produces a much more concave kind of shape, which is much more conducive for a optimized gradient descent algorithm. Right. So I had a k nearest neighbors video here. It's 2 minutes long. I just feel like it would explain k nearest neighbors very well. Can you just tell me if you can hear the sound?
K-nearest neighbor is a super simple supervised machine learning algorithm that can be solved for both classification
Cool.
and regression problem. Here is a simple two-dimensional example for you to have a better
Also, if you
understanding
had
of
any
this
questions
algorithm.
about the previous bit, let me
Let's say we want to
know.
classify the
Oh,
given
you can
point
hear it
into
twice. That's
one of the
probably
three
from my
groups.
mic.
In
Okay,
order to find the
hold on. Let me turn off my mic.
k-nearest neighbors of the given point, we need to calculate the distance between the given point to the other points. There are many distance functions, but Euclidean is the most commonly used one. Then we need to sort the nearest neighbors of the given point by the distances in increasing order. For the classification problem, the point is classified by a vote of its neighbors. Then the point is assigned to the class most common among its k nearest neighbors. K value here controls the balance between overfitting and underfitting. The best value can be found with cross-validation and the learning curve. A small k value usually leads to low bias but high variance, and a large k usually leads to high bias but low variance. It is important to find a balance between them. For the regression problem, we simply return the average of the k nearest neighbors labels as the prediction. Here it is a simple code example. We use a very famous Aries dataset and only take the first two features for demonstration purpose. The k nearest neighbor algorithm is from sklearn, and it is self-explanatory. I encourage you to try it yourself with different parameters. These two plots are
Right. In the interest of time, I don't think the rest of it's very relevant, so I'm just going to move on. So from that, like it was just a recap of k nearest neighbors. All it is it's a instance based classification or regression. You can use it for both, but um, for the purposes of like the rest of this lecture, I'm just going to call it classification because it's what it's more commonly used for. So it's instance based, so it looks at the specific data points that it has in its training set. It doesn't create like a model, as per se, like with the other ones, with the other algorithms like logistic regression, linear regression, all of the ones that we looked at. It creates a model. With this one, it doesn't really create a model. It just relies on the data set it's been given, and you have to keep the data set, the entire data set, with the model in order for it to work, which is not the case. When you have trained with linear regression, logistic regression, when you train it, um, you can pretty much get rid of the training data and then just have the model work. But with this one, you got to keep the points, the data points, because the data points is what's used to make the classifications. It's kind of like a voting system. The class of a point is determined by the vote of its k nearest neighbors. K would be a constant value. So, like if k is 3, it would be determined by what is the class of the 3 nearest neighbors to that data point that we got as an input. And that's why it's called instance based. It's also lazy. Like officially, I'm not saying that as an insult. It's a lazy algorithm because it goes with the nearest amount first, and it doesn't analyze the whole thing. It kind of just gets the shortest and quickest possible answer. Right. Hence, it's not always optimal. It's more like a heuristic. Right. Let's move on.
a real visualization
Can
from
I skip the video? Okay, cool. Just gonna check that the mic. Can you? I did unmute myself, right? Oh, I think I did, right? I muted myself. Okay. Yep. Okay, cool. Uh, Types of computable distance. I hope you remember this. It's just Minkowski distance, Manhattan distance, Euclidean distance. I'm not going to go into this too much because at the end of the day, they're just formula. I think the only one you really need to know is Euclidean distance, maybe perhaps Manhattan distance in some rare cases. God knows what they use Minkowski distance for, but like Euclidean distance, make sure you remember that one. Take a screenshot of this page. It's basically formulas. Yeah, never. I don't know what it's used for. I honestly don't even think it's worth remembering. But definitely remember Euclidean. Uh, yeah, definitely remember Euclidean. That's the Euclidean's also quite easy to remember. It's basically just like what we did, like mathematically. You can think it's just the sum of the differences, right? We're trying to work out what the difference is between. We're trying to work out a distance between 2 points. We're just doing a minus, squaring it, and then we sum all the distances, right? And this gives us the k number of nearest neighbors. All right, cool. Let's move on. So this would kind of be more valid when we use KNN for regression. So remember how this KNN can be used for classification and regression. It's not really too important to work out multiple distances when you're doing classification because you just look at the nearest ones. Just take one distance, and which is just x minus y plus, sorry, x minus x1 plus y minus y1 all in the square root. That's how you'd work it out. Um, Whereas when you're trying to do regression, you'd use this because you want to find out an exact continuous point that you want to place that based on its nearest neighbors. All right. This is the last slide. So, oh, Manhattan is just one. Why is he? Okay, yeah, okay. Uh, After this, there's one more slide. Actually, my bad. There is the second to last slide. Cool. Um, the k value is just the number of nearest neighbors that the model will take into consideration when deciding the class of an input. Um, so if the k is 3 and you slap a data point onto the model, it will look at the 3 points nearest to it and use the class of those points to judge what the class of the input point is. So, just like how learning rate as a hyperparameter played a role in the result we got from gradient descent, k as a hyperparameter of k and n plays a vital role in the output as well. So a low k value, aka we barely take any neighbors in, so we might take 2 or 3 neighbors off the point, is overfitting to the data. And this might seem counterintuitive, but the reason it's overfitting is because it only looks at a few select data points, and just those values will be used to classify it. And as we know, those values could be very well outliers, or they may not be representative of the general class or of that region. So if your KNN in the extreme case, let's say k is 1, so it only looks at its 1, so it only looks at its like nearest neighbor, just 1 point. And you have a point on your data set full of class B. However, there is one outlier, a class A dot, and your input just happens to be next to that outlier. It's going to get classed as A, even though it's surrounded by B's everywhere else. So is what a very low k value would be. It would lead to overfitting, too specific on the training data, way too specific on the training data, and therefore bad for generalized cases in the real world. However, a high k value will also be bad because that would lead to underfitting, and as it will take into consideration way too many values when deciding the class of the input, even if those data points are quite far from it. So if we have a k nearest neighbor full of class A, class B dots, and say we have the k value as 100, and there are only 50 like points in its own class, it's then just going to like take the nearest neighbors from the other class, even though that they're quite far away, and therefore lead to a very underfitted model, as it will lead to it kind of using the entire data set almost to make this one prediction. And in the extreme case, it'll literally just be like in the data set, which class has more data points. So we don't want it to be that either. Hence why we need to find the right k value so we don't result in underfitting or overfitting. In this case, it's nothing to do with epochs, which is what it's to do with when we are looking at linear regression and logistic regression. Does k nearest neighbors and the effect of the k value make sense? I'm going to have a 10-second period for anyone to say, hey, have an objection. Does anyone object to moving on? We had no objection, Your Honor, so let's move on. Uh, final slide. Okay, wait. Final slide is the slide after this. I promise. I promise you it's the slide after this. Okay. So very versatile. So why is k nearest neighbor good? It's very versatile, classification or regression, and it's non-parametric. Remember, so it doesn't come into the model with any assumptions. It just does whatever's best. It uses whichever number of parameters it feels is best, nothing assumed to start off with. And it can be used for classification and regression, so there is nothing it cannot do. It's also easy to implement, very easy to understand and interpret. We learned from that guy in 2 minutes what it was. And it can also approximate complex functions. It has very good accuracy. Cool. However, There's no free lunch in the world of machine learning, so it comes with its downsides and drawbacks as well. So we need to specify the distance function and predefine a k value. It has to store all the training data and needs to calculate the value of new points based on the training data only. It's also very sensitive to noise, especially when the value of k is small. So remember what I talked about small value of k using causing overfitting? It's because when we have noise, aka outliers, kind of, and like incorrectly placed things in the training data, it will lead to like a lot of misclassified tests as well because it's very sensitive to noise. It only relies on what's around it, especially when k is small. So we can't have um, bad quality slash noisy training data for KNN. It's simply not an option. It would just it's really sensitive to noise. And then finally, its performance is degraded greatly as the data's dimensions increase. You can imagine having massive data sets like that for it. Okay, cool. That's KNN. That's the pros and cons. So now you know when to use it and when to not for all the things that you're going to be doing. Cool. Feature scaling. Okay. Next slide is actually the last slide now. As in, this is the last slide. This is the last slide. This is the last slide. Okay. Feature scaling is a set of techniques used in data science. Do you want it to be an exhaustive, complete lecture on machine learning, what's it, supervised learning, or not? So I had to kind of like put everything in. It's a lot of content. Um, it's literally just this. This is it, feature scaling, and then it's done. So feature scaling is a set of techniques used in data science to manipulate the impact of manipulate the impact and range of certain features so that models give each of them an appropriate level of significance. And there are two methods for feature scaling. There's normalization and standardization. So you may have remembered from our WECA assignment a couple of weeks ago, we did normalization. Um, and and this is how normalization works. This is the formula here. There's nothing really more to it. Just put it into the formula, and you have a normalized data set. By minimum and maximum, it actually means the global minimum and the global maximum. So whatever the lowest value is in your entire data set and whatever the highest value is in your entire data set, you'd go with those. And by dividing it by that, you end up with all of the values between 0 and 1. And then standardization means that there's a set mean and a set variance. So you may have remembered this from A level. If you did A level stats, well, you would have because everyone did A level maths here. You did the standard normal form, which is when you had a mean of 0 and a variance of 1. That's what this formula does. You will remember it from the formula sheet at A level, where standard normal is calculated, except at A level it was called Z. Here it's just different notation, but it's the same formula. You standardize everything so that its mean of the data set is 0 and the variance is 1, aka something within one standard deviation squared is 1 from statistics. However, we normally use normalization, no pun intended, and I hope that's also simpler to understand. Uh, I think. Does anyone have any questions about feature scaling? The reason it's important is because we can often have data sets with wildly different scales. For example, if we're talking about, let's say, I don't know, values, some kind of values that don't really deviate, don't really go above 10. And then we have another value like distance, which can be like thousands of meters, right? Um, Naturally, we don't want to give the distance 1,000 times more importance than we give the first variable, which only goes up to 10. Hence, we feature scale them all down to be between 0 and 1, so they're all treated with equal importance when the machine learning algorithm looks at it. You can, in fact, actually tweak this function in like AI2 next year, where we can adjust it so we can, if we know that some values, some features are more critical and more relevant and important to make a prediction than other features, then we can actually feature scale that so that those features are exaggerated and the less relevant features are, you know, sh- less range, and that will kind of tweak. That's what fine tuning does in machine learning. We can fine tune the data set. But yeah, that's feature scaling for AI1. Finally, the slide you've all been waiting for. Hey, we're done. We're done. We're done, guys. How are you feeling? Are you guys got all of it? You guys got any questions? Any questions, guys? How many people? How many survivors do we have in the call right now? We have 9 survivors. Congratulations to 9 of you who stayed until the very end. Good job, guys. But that is an exhaustive list. I'm pretty sure YouTube won't allow us to like upload it. Maybe they will, but we might have to split it up into 2 videos. I definitely had to split my recording up into 2 videos because of the maximum 1 hour recording limit on CapCut. But remember, train your models, punish your models, use lazy models responsibly, and pay the cost of your models. Exactly. What a great summary. We summarized the entire lecture in 2 seconds. Did you manage to fix the recording? I did, in fact, manage to fix the recording. It is still recording right now, so I should probably go ahead and end that if there are no more questions. So, are there any questions before I end the recording? Any valuable input that you guys want? I'm not seeing any questions, so I will call it a day. Thank you guys for watching, and I'll be in the VC from now on. If anyone wants to discuss anything or has more questions, just go to the VC. Thanks, guys.